Okay, a couple of new pieces to add to our nuclear unit today. One is to talk about particle accelerators. So, up until now, we've talked about spontaneous radioactivity, where there are naturally occurring in our world atoms that are not stable. And so, in order to become stable, they emit subatomic particles in an attempt to get their nucleus to be stable. So, that's called natural radioactivity or spontaneous radioactivity or natural radioactive decay. But being human, we sometimes like to see if we can instigate things. And if if you were a kid and got like a remote control car for Christmas one year, and maybe you were driving it around your house and you weren't all that good at it at the beginning, and maybe at one point you drove it into the wall. And when it hit the wall, its wheels probably fell off, pieces probably fell off, and as a little kid you were probably upset with your bottom lip trembling, and then some adult probably said, no, don't worry about it, it's supposed to do that. And then they picked up the pieces and they clipped it all back together and they gave it back to you. And you were like, it's supposed to do that. And so then you did what any little kid would do. You drove it into the wall faster to see if more pieces would come off, and faster and faster. So that's kind of what we do in nuclear physics. We make things, we create these pieces of equipment called particle accelerators, and their name is very telling. They accelerate particles. So we make them to speed up particles, and after the particles are sped up, then we fire those particles at a sample of material, right? So that particles are coming in at high speed, they hit the sample of material, and then we collect the things that come off. We collect the things that come off as a result of the collision, hoping that we'll discover some new subatomic particle never seen before. Okay, so that's the whole point of a particle accelerator. And of course, when we first started to do this, it was great and we found some new subatomic particles. So then we did exactly what the little kid would do. We wanted to speed them up faster to see if we could get different particles, and faster and faster. And even today, we are building bigger and better particle accelerators so that the particles will hit the sample at a higher speed, so we can try to figure out to see what new things might be created or given off. Even in Europe, there's one where they collide these high-speed particles together to see what will happen. Okay, so particle accelerators. Most often they use electric fields and magnetic fields to increase the kinetic energy of the charged particles, and usually they need to be charged, so we're talking electrons, protons, alpha particles. They're always sped up through an evacuated tube, right? So even though I'm going to tell you in a few minutes about how huge these particle accelerators can be, huge in the sense of length or diameter, the tube itself is not that huge because it needs to, like in the sense of this way, it's long, but it has to be evacuated because you don't want these particles that you're speeding up to be running into air molecules. Okay, and then again, of course, the idea is that then in the collision, something new will be created. Now, examples. Probably one of the first particle accelerators was the linear accelerator. And again, its name gives away a lot about it. It is a straight line. So, the first ones would have been fairly long, fairly decent size, but we kept making them longer and longer. There is one now in Stanford, California, that is 3.3 kilometers long. Okay, so that's a pretty good distance for a linear accelerator. Of course, it didn't take very long before people realized, you know what, it takes a long time to go this whole distance, and we need to buy a lot of land to go 3.3 kilometers. What if we were to curve it? And so now a lot of our accelerators are circular. And so they're called synchrotrons. Okay? And these guys can be up to up to a 2-kilometer radius. So for 12, so we're talking like 12 kilometers around in the circle, which is a lot better that it's circular than linear. Okay, one of the first ones was probably the Fermi. It's in Chicago, the Fermi Lab, named after Enrico Fermi. I actually tried to go in and visit when I was studying Chicago, but they thought I was a Canadian spy and they wouldn't let me in. There is a great picture of one on page 626 of your textbook, if you have it with you, and it's the Fermi Lab one. So it has a diameter of 2 kilometers, that one. There was a huge one being built in Texas. They were in a race to discover some subatomic particles. They were building one at the same time in Europe, the CERN. The Texas one was to be 88 kilometers in circumference. However, the CERN was built first. The CERN discovered the subatomic particle the Texas one had been hoping to get. Funding was cut in the Texas one and it was never finished. So somewhere in Texas there is an unfinished 88 kilometer circumference ring that isn't done. And then more recently in Europe is the Hadron Collider as well. Okay, so all of these would be huge particle accelerators. There are some smaller ones. They're called cyclotrons. And cyclotrons can be handheld. And they're really like a double D on either side with a gap in the middle. And so the particle gets accelerated here, and then the gap has, I think it's different electric fields on it. So it gets sped up around the electric field, goes around, gets sped up. So it gets sped up, I believe, in the gap. So these ones are pretty tiny. Probably 1930 was when these ones were created. Okay. And then there is a Van de Graaff generator accelerator. The Van de Graaff generator like we have in the class, but it's used to speed up particles. Okay, so what would I expect you to know about the accelerators? I'd expect you to know that they're used to speed up particles that are then used in collisions to try to find new subatomic particles. I'd expect you to recognize their names. But I wouldn't expect you to write a big thesis or anything on them. So those are particle accelerators. Back up here when I was talking about them, I said, but we also then need something to detect the particles that are given off. And so we also have something that are called particle detectors. And again, their name tells you exactly what they're doing. So we would put them around our experiment so that we could pick up the particles going off in any direction. Even Rutherford had these with his alpha particle scattering experiment. Again, one that I've already mentioned a couple of times in this course is a Geiger counter. And a Geiger counter, most of them that I know of are kind of handheld. They'd remind you of the handheld device that when you walk through security and you have something metal on or in your pockets and you set off the things and then they come over with that little wand and they run it over your body. That's kind of what a Geiger counter is. And I know about it best from when I was doing my research for my thesis in Chalk River, because one night when I was there at 2:30 in the morning changing the conditions on my sample that I was shooting neutrons at, because that was what my thesis was on, I was lying on the floor of the nuclear reactor, and I was there because I needed neutrons, and they happen to be a byproduct of nuclear reactors, which we'll talk about in a couple of days. Anyway, I was lying on the floor, fixing my apparatus, got up off the floor, and went to leave, and in a nuclear reactor, they have a series of different monitors that you have to go through on the way in and on the way out to make sure you haven't been exposed to too much radiation. And so the first one, at the doors of the reactor hall, I set off all the alarms So these guys in hazmat suits came down with handheld Geiger counters and were running them over my body, deciding what pieces of my clothing they were going to take from me because they were contaminated.